Maybe tell us a little bit about how you got the job at Hughes.
Yeah, so Hughes was sending me the samples. Hughes, of course, was number one in the world in sending satellites, government satellites. And they sort of worked, they provided the samples. I was working. At Hughes, the deal was if you send a satellite and it's supposed to last there for 3 years, but you can have it in space for 5 years, the last 2 years were like a free satellite. The bonus scheme was if you could keep it longer in space, there's a huge financial incentive to do so. So they really wanted rad-hard circuitry, LSI. Hughes wanted to do for satellites with MOS LSI what IBM did with 360 with LSI. Basically integration of a lot of SSI components into 2 chips. And we had a redundant 2 chips, and that was a satellite basically. It was on sapphire, silicon on sapphire. Anyway, so at Hughes, I got a job at Hughes, and basically, so long as I was doing my rad hardening research and building devices on sapphire, I could do basically anything else that I wanted to. So that's kind of Hughes. Now, Hughes had a phenomenal, this is in Newport Beach, Microelectronics Research Center. I was a member of the technical staff, and they had a phenomenal pilot line. And I became a very good process engineer because I was my own technician. I could go in there, I could do whatever I wanted. And I just loved, looking at a microscope and seeing how I could, it was just great. I didn't have to ask anybody for permission, and I could do whatever I wanted, and that was really great.
Great. So we see this patent that was filed in 1977 for the first Fowler-Nordheim tunneling floating gate EEPROM. So this was probably the essential, could you describe this as the essence of what you were doing at Hughes and,
right,
and how it affected everything else thereafter?
Right, so this, the years really 1976 to 78 were, in my opinion, very pivotal, in my opinion, to the flash memory industry. First with E2PROM and then flash E2PROM. Because in 1971, Doug Frohman invented EEPROM. And EEPROM was, as you know, electrically programmable but UV erasable, 15 minutes under the UV light. So everybody in the world was looking for an electrically erasable EEPROM, including myself in my spare time. And in addition to that, I was working on the side on all kind of other patents, like reflecting flea collars and
things with more short-term sales?
No. I just was intrigued. I learned how to file patents, how to write patents. I went to Washington and studied the patent library. In those days, there wasn't search engines and stuff like that. So one day, my wife says to me, our kitchen became like a lab. I think, I think you're familiar with those labs, yeah?
I think you're talking to Ted Hoff over there, yes.
So I was trying to invent a fishing rod that you wouldn't have to cast overhead, and I wasn't getting anywhere. So my wife says to me, how many people are there that go fishing? The number was 26 million. And how many times have you gone fishing? I went once, and I never caught a fish. All right, so among those 26 million, she says, don't you think there's enough tinkerers out there that they would have already thought about anything that could be invented? And I said, yeah. And how many people know about the work that you're doing? She didn't know Fowler-Nordheim. And I said, well, maybe 3, maybe 5. So she says, so what am I missing here? Why? So it was really my aha moment, because I said, it's like, wow, why didn't I think of that? Anyway, so from that day on, I stopped tinkering with anything except in what I knew. And within 6 weeks of that time, I came up with a concept that if I could, in those days, the EEPROM had 1,000 angstrom gate oxide, 1,000 angstrom, 100 nanometers today. So if you wanted to use Fowler Northern tunneling for program O arrays, you'd need to apply over 100 volts to make it effective. So the idea was very simple. What if I thin it down? Well, people had talked about that before. Bell Labs was talking about 50 angstroms tunnel oxide, but 50 angstrom was too little. Basically, you could program, but all the charge on the floating gate would escape because it was direct tunneling rather than Fowler Northern tunneling. So my wife and I and our little daughter were traveling to a conference in Colorado, and I'm driving there, our Datsun 510, and suddenly it hit me. I said, if I can go the Goldilocks thing, not too thick, not too thin, just right. So just right, I said it was somewhere between 35 angstroms and 150 angstroms. I don't know where, but it's somewhere in that range where I'm going to get what I need from Fowler Nordheim, and I'm not going to lose my charge. So this was 6 weeks after that fishing rod thing, and within another 6 weeks or so, I was able at Hughes to fabricate floating gate capacitors. That was a oxide. I etched a very, very small hole in that oxide, grew different thicknesses of SiO2, then put a polysilicon, doped polysilicon, etched it. It was like a 4 mil diameter hole with a 25 mil capacitor, and then I put a dielectric on top of that, and then an electrode. And that was my floating gate capacitor, and immediately it did not all thicknesses, but at around 100 angstroms, it programmed beautifully, and it erased beautifully, except that I immediately saw that I was also injecting charge from the control electrode. So I knew that I have the right thickness for the tunnel oxide for Fowler Nordheim tunneling, and I knew that I needed to have a blocking dielectric on the other side, so when I erased, I would be able to just erase the charge rather than also inject new charge from the other electrode. So that started. I went to my boss. I said, "Look, Tom, here's the data." Tom Toombs was the head manager of the research center. I said, "Look, this looks very promising. We've barely scratched the surface." This was looking at thresholds, V flat band, capacitor flat band. I could move it this way, move it this way. It would stay there for days at 250 degrees. Then I could move it back, stay there. I could move it back and forth, back and forth. It was unbelievable, really unbelievable. So Tom said, "Look, we're not doing any non-volatile memory here. We're working on radiation hardness and integration. But yet, I think you should do it. You should continue." And he gave me a technician, and I set up and I said, this is not going to be just a 1 week project. This is going to be a long time project. He said, "Yes, go for it." So it took me 2 years of, we had over 10,000 samples of SiO2 of all thicknesses, of all ways of thermal oxidation, annealing, deposition, you name it, and we did it. And then I started basically not using a capacitor, but actually measuring currents through thin oxides, thin in the range of about 100 angstroms. And that brought me to the realization that actually the endurance was going to be limited. Again, to give you perspective, in 1976, MOS transistors were still relatively infant and not very, not immune to pinholes and things like that. Yields were not very good, surface conditions were not that good, impurities and things, instabilities, contamination, boron, you got all kind of stuff. So to go from 1,000 angstroms to 100 angstroms was like heresy. you're crazy. We can't do 1,000 angstroms. You're telling us about 100 angstroms. But it had to be 100 angstroms because I knew I couldn't go above 20, 25 volts. And that's what it took to go from 1,000 to. So I discovered that, yes, that Fowler-Norman tunneling was very good, very reproducible, incredibly reproducible. But there was a distribution, of course, a normal distribution. Some oxides broke down after 100 cycles, some after 10 to the 7 cycles. And depending on how you grew the oxide, you could get to about 1 million cycles, right array cycles. This was far from optimized. But I realized I needed to find ways to characterize these films, so I developed a setup that allowed me to measure the current through thin oxides, Fowler-Norman tunneling current, and compensate for any trapping of charge. Virgin oxide does not have deep traps for electrons. These deep traps are generated as you program. During programming, you create broken bonds, silicon-oxygen bonds, and these are deep traps in the forbidden gap of SiO2, and the electrons that come in, some of them remain in the glass, in the SiO2. They don't make it through, and of course they are negatively charged, so they start opposing new electrons coming in, and that's why you have window closure in a device. So I said, fine, I understand I'm trapping charge, but I want to see when I'm actually breaking down the film. And to do that, I said, I'm going to increase my voltage automatically to compensate for trapped electrons. That will tell me at the time of breakdown how many electrons I've got are trapped. I can figure out where they're trapped actually, and also it will give me an idea of what is the time to breakdown of that oxide. So the combination of TBD, time to breakdown, and QBD, the amount of charge that you store in the oxide at breakdown, were two key parameters that I could characterize films by, and that in fact proved two things. First of all, Fowler-Norman tunneling works. It's extremely efficient for programming and for racing. Extremely, I mean, 1 million times more efficient than hot electron injection. Every electron that you tunnel is captured, except for very, very few that are deep trapped. But that you have this limited endurance, that every cycle, program and erase, you are bringing the demise of that device closer to breakdown. And of course, breakdown is terrible. I mean, it's catastrophic. So, this then led to developing this device here, and this is the first practical floating gate EEPROM. It's practical because for the first time, he taught about very thin oxides, and I limited the thin oxides to a very small area to avoid any imperfections, and more importantly, or equally importantly, to get the right coupling ratio between the control gate and the floating gate on the one side and the floating gate and the substrate. So it was very, very important to have relatively very strong coupling between the control gate and the floating gate, so that you basically, the floating gate would follow very closely to where the control gate is. So I did two things. First of all, get the right ratio of areas to get the right coupling ratio. It was 70% or so. And I introduced a blocking dielectric, which was SiO2 capped with silicon nitride. And the reason why I picked that is because Hughes' production line for watch chips was making MOS 10-volt transistors. For watches, it was 1.5 volts. But their process was aluminum gate. They didn't use polysilicon. And aluminum gate had problems, so they put a little bit of nitride to protect the oxide. So I said, well, you could do this. Can you put this oxide plus nitride? And it worked. So it was just everything falling into place without me being smart enough to expect it in the first place. But so Tom said, look, why don't we, actually I said that to Tom, but Tom said, yeah, why don't we design a chip and commercialize it? And we picked the Intel 8 kilobit NMOS EEPROM. So we designed this pin compatible CMOS EEPROM, and that was the first EEPROM, and Hughes developed it and actually sold it. We hired a guy, Frank Wanlas. I don't know if you know Frank Wanlas, but Frank designed this chip together with two people at Hughes, two circuit designers. But Frank Wanlas invented the CMOS inverter, and was an incredibly brilliant guy. So he designed this chip for us, and that was the first chip that we actually sold. The first chip that we actually commercialized using the floating gate Fowler tunneling was actually a 256-bit NOV-RAM, non-volatile RAM, an 8-transistor static RAM with with a normal 6 transistors, and the 7th one was a non-volatile transistor. And if you lost power, you basically, before you lost the power, you'd raise all the voltages, and that transistor would be programmed to one state or the other, and when you powered it back up again, it would power the latch in the correct. So the most important thing about this work, which I published at the Journal of Applied Physics, a 15-page article which was used for many years by people that were developing EEPROM and in the early days of flash, and is used today, of course, across the board. All NAND flash uses the same thin tunnel dielectric, the same tunnel arrays, tunnel program. The first NAND flash, in fact, did not use this and was going nowhere. First NAND flash was using hot electron injection for programming, and that was really, in a serial device, it's really horrendous to try and do that. But when they went to tunnel program and tunnel arrays, that's when NAND really started shining. But my lessons from this that I took with me for the rest of my career was tunneling works, tunnel oxide works, but it has limited endurance, and you cannot tell which transistor will fail first and which will fail last. So you have a distribution, and if you start cycling too much, you're going to start, some of your cells, your bits are going to get lost, and you will overwhelm eventually any ECC. You're just going to walk up. So, and that really led to, later on, in my mind, the requirement for a system flash solution. I think we'll talk about it.
Right, and system flash is the work that basically SanDisk was founded on. That was the work that allowed flash to be a usable device for data storage.
Right.
Yeah.